Good morning. This is the fourth unit about distributions of random variables. And in this video, I'm going to talk about continuous variables, the density function. Okay, so continuous variable is the case when we have values measured in a continuous scale with decimals as a result of measuring or evaluating a physical magnitude. The rule is that every time that we have values with decimals, it means that they are measured in a continuous scale, although sometimes we have values without decimals, but they can also correspond to a continuous scale if the values are rounded. For example, the weight of a person, usually the values are expressed without decimals, but it is a continuous variable because if I express the values in grams, or in kilos, but also with decimals, that makes sense. Okay, actually, usually we don't know the value with so much accuracy, but it is not nonsense. So it corresponds to a continuous variable. Or if we have electric power from a machine, or time is also always continuous. I can express the time in hours, minutes, seconds, and milliseconds. So in general, the values of random variables can be obtained by counting or by measuring. If I count, it becomes a discrete random variable. If I measure, it becomes a continuous random variable. So that can be a rule. So the variable can take any of the infinite values from an interval. So important, very important. When we say in statistics that we are dealing with a continuous variable, we're assuming that the variable is measured with many decimals. It is like an assumption that we make in statistics. For example, if I say, what is the probability that a continuous variable takes the value 3? Okay, so if I say that it is continuous, then I assume that it is measured with a lot of decimals. A lot of them. So let's think. Imagine that I measure values in a continuous scale. What is the probability to have exactly the value 3.00000, all the decimals being 0? Okay, so this probability tends to 0, and this is very important that you understand it. So once again, if we are in a discrete variable, okay, being less than 3 or less or equal than 3 is different, but in a continuous scale, the probability that a variable takes a specific values, we will always assume that it is 0 because of this explanation. Okay, so if it is continuous, less or equal than 3 is equivalent to being less than 3. But if it is discrete, it's not the same. So imagine that then I have values of height, and if I ask a set of people about their height, usually I will get the information without decimals if it is measured in centimeters, because people are not able to provide this information with too much accuracy. We don't know our height with millimeters usually, okay? So I can ask, what is the probability to find a person with a height of 170 centimeters? Actually, is this probability 0? No, obviously not. For sure, we can have people that answer this. What we mean is that in this case, the values are rounded. Okay, so we have to imagine that we have values measured with decimals, but the values are rounded. So to be equal to 170 means a rounded value of 170 is equivalent to being a value between the interval 179.5 until 170.5. Okay, now let's talk about the density function, which is an important concept in continuous variables. And then let's start with the concept of histogram. The histogram is a graphical representation of a dataset For example, this is a possible example of a frequency histogram. So I have data which are grouped into intervals, and then here we have a vertical scale which can be absolute or relative, okay? And then based, so here more or less I will have the minimum, here I will have the maximum, and then this shape of the histogram provides us with very important information. For example, if the shape of the histogram is symmetric, we will say that the distribution is symmetric. If the shape of the histogram is skewed, we'll say that the distribution is skewed, and so on. Okay, and then the number of intervals is obtained more or less as the square root of n. Of course, if I have very few intervals, less than 5, it provides very few information. So I need like a minimum number of values, like 40 or 50, to provide a histogram with good enough information. So now the density function, it is for continuous variables. It describes the shape of the histogram. That would be like a practical definition. The density function is the function that describes the shape of the histogram. For example, imagine that here I have a histogram. In this case, this is a special histogram because the total area of the bars is 1. So, for example, between imagine that I have a sample size of 40 values, and then between 30 and 40, I have 15% of the values, so that the area of this bar is 15% of the total area. Imagine that now I increase quite much the sample size, the number of values. Imagine that now I have 40,000 values. It allows me to increase the number of bars in this histogram, and then I can have a histogram like this. But then, if I want to calculate the probability or the percentage of values which are comprised between 30 and 40, that would be the same. I should sum the area of these bars in orange. Okay. Then now let's go to the limit case. Imagine that I have like infinite bars. Then instead of having this kind of bars from a histogram, I have a curve. Okay, this curve describes this shape of the histogram. This curve is called the density function. Okay, so I like this kind of definition, which is more or less easy to remember. Then, how will we calculate or compute the probability that the variable is between 30 and 40? This will be 15%, which is the area in orange. Then that will be the integration. This is the density function. Then the area under the curve is 1. This is very important. For any kind of density function, the rule is that the area under the curve is 1, or the integration from minus infinite to infinite has to be 1. So the probability is computed as an integration. Remember that the integration is the area below the curve, so the integration between 30 and 40 of the density function will provide me with this kind of probability. Okay, so the density function models the pattern of variability of continuous variables. Okay, so for example, in this case, imagine that this area in blue is 37%. Okay, it allows the calculation of probabilities in any interval. Okay, this interval will be the area under the curve, which corresponds to integration of the density function. Okay, so this is an important. Okay, if we know the density function, if we make the mathematical integration between a and b, okay, so we will have the probability between a and b. Okay, and remember the rule that I was saying, the area under the curve always is 1, so the integration from minus infinite to infinite has to be 1. Okay, then another concept. Remember that in another video I talked about the concept of distribution function, and the definition is the probability of the random variable is lower or equal This is the same concept for discrete distribution. This is the same concept for continuous distribution. In this case, to be lower or equal to value is the integration from minus infinite to that specific value of the density function. Okay, why is it called density function? Well, the probability that belongs to a differential interval, okay, so imagine that we have just a small, very narrow interval, okay, so the base is a differential of x, and so the probability will be the area, which is the base multiplied by the value of the density function. Okay, this is the probability. So I can put this mathematical expression. The density function is a probability divided by a differential of x. This is like a density of probability. So basically this is like the reason why it has this special or strange name, density function. Okay, well, so this is not too much important, but I like explaining this to explain why it has this special name. Well, what is the most famous density function? The one that I'm showing here. It is the Gauss-Bell. It corresponds to a normal distribution, which is the most common or the most normal distribution that we found in practice every time that we measure values of a physical magnitude. Okay, this is the Bell developed by Gauss. Gauss was a mathematician who proposed the mathematical expression of this model, and this is why it has this name. Okay, and then what is the utility of the vertical scale? Well, actually, there is no much utility because the interest is in the area. Remember that the area, the total area is 1, so we make integration and then we obtain the area. For that reason, the vertical scale is not of much interest. Okay, so now let's make an exercise. Imagine that the minimum value of a distribution is 0 and the maximum is 10. Then imagine that the density function has a triangular shape and the mode is 4. Okay, so then the question is to obtain the mathematical equation of the density function. Well, this is a picture, okay, which you can see that 0 is the minimum, 10 is the maximum, and 4 is the mode, and the shape is like a triangle. Remember that the definition of the mode is the value where the function reaches the maximum value. Okay, so if that would be like a histogram, so around 4 we would have the highest bars. Okay, so this is the shape of the density function, but we need to obtain the mathematical equation. So the area of this triangle has to be 1. So if we multiply the base by the height of the triangle divided by 2, which is 10 by a value that we don't know divided by 2, it has to be 1. So it means that the height of this triangle is 2 divided by 10. Okay, so this is a value that we obtain mathematically. Okay, so based on this information, we have this straight line, so we have to derive the mathematical equation. Well, this is something from the area of mathematics, not statistics. So I'm giving you the solution. The solution is 0.05 multiplied by x. When x is 0, the function is 0. When x is 4, you can check that the function is 0.2. So it makes sense. Then what happens for this second line? Well, you can think about that. You can apply your knowledge about mathematics to derive the mathematical expression, but I'm giving you the solution. Okay, when the value is 10, 10 minus 10 is 0, so this becomes 0. And when the value is 4, you can check that the function reaches the same value of 0.2. So this would be the density function. Okay, so another equation that we can make with this exercise is to obtain the first quartile. So by definition, the first quartile is the value so that the area below will be 0.25. So as we have the mathematical equation of this line, we know that the integration between 0 to this first quartile of the density function will be 0.25. Okay, so solving this expression, this mathematical expression, will lead to the calculation of the first quartile. So we make the integration. Okay, you know that the integration of x is x squared divided by 2. Then we apply the rule of Barrow. Then we put x squared being equal to q1 minus x squared being equal to 0. Then this is multiplied by this constant, and then finally we solve q1 making the square root, and this is 1. Okay, so this is an interesting exercise, and here this is the solution. I recommend that you practice and you think about similar exercises, because in the exam you can have exercises like this one. Okay, now let's think, is the median equal to 5? Okay, remember or think about the definition of the median. Median is when we have data, a set of data, we sort from the we sort from the lowest to the highest, and then we find the value which is exactly at the middle. By definition, this value is called the median. In this example, the minimum is 0, the maximum is 10, and so some people can say, well, 5 is in the middle between 0 and 10, so 5 can be the median. Well, no, that is wrong. That is not the case. We have to find a value so that the area on the right side is 0.5. I think that graphically we can see very clearly that this value is going to be higher than 4, so that we have to use this mathematical equation of this second line. Okay, so now in this case the integration from this second okay, the median corresponds to the second quartile. This is why here I'm putting Q2, which is second quartile. So the integration from this second quartile to 10 of the expression of this density function has to be 1/2. By definition, this is the concept of the median. Okay, well, so the integration of this is this one. So 10 minus x squared divided by 2. Then we have to apply the rule of Barrow. We make this expression equal to 10 minus this expression equal to q2. So we solve, and then finally we get that q2 is 4.52. So we can check that the value is less than 5. So again, this exercise is interesting, and for the exams, I think that easy, polynomial expressions easy to integrate could appear. Okay, and another question is obtain the mean. So here we obtain the median, but is there any way to obtain the mean? Well, it is possible, but we know another method that I will explain further in another video. So, well, here I finished in the unit 4 about continuous random variables. I finished this video about density function. Thank you for your attention.